In this work, we introduce Self6D, Self-Supervised Monocular 6D Object Pose Estimation. This is a joint work from Gu Wang, Fabian Manard, Jianjun Shao, Xiangyang Ji, Nasir Nawab, and Federico Tombali. 6D object pose estimation from a single RGB image is essential to many real-world applications in computer vision, such as robotic manipulation, augmented reality, and autonomous driving. CNNs have recently proven to be capable of predicting reliable 6D poses from monocular images, but are also identified as extremely data-driven. Furthermore, acquiring real-world 6D object pose annotations is very time-consuming and labor-intensive. So how can we overcome this problem? There have been several works aiming to tackle this problem from the perspective of domain adaptation. In 6D object pose estimation, knowledge transfer from the synthetic domain to real one is often achieved via GANs, feature mapping, or domain randomization. However, we can argue that these methods do not make full use of the information available from unlabeled real data. Since it's easier to acquire unlabeled real RGBD data, to this end, we want to tackle this problem from a very different viewpoint by making use of self-supervised learning. Our work is inspired by recent works on self-supervised or weakly-supervised learning for related computer vision tasks. Self-supervised learning is commonly achieved through enforcing consistencies such as pixel consistency across multiple views or modalities. For example, in monocular depth estimation, one can enforce the left-right consistency by warping the pixels from one view to another. In 3D human pose estimation, the self-supervision can be achieved by multi-view geometry or 2D-3D consistency via key point lifting and reprojection. In 3D object reconstruction and human body reconstruction, self-supervision can be enforced by leveraging neural rendering and optimizing the 2D losses. In the domain of 6D object pose estimation, self-supervised learning is still a rather unexplored field. Deng et al. Proposed a self-labeling pipeline to collect training data with an interactive robot manipulator and obtain 6D pose labels by running several methods for 6D pose estimation. However, their methods are RGBD-based, and in its core, the pose estimation module is still trained in a fully supervised manner with self-labeled training data. We propose Self6D, a self-supervised learning approach to overcome the problem of lack of real annotations and domain gap in monocular 6D object pose estimation. To the best of our knowledge, we are the first to explore self-supervised monocular 6D object pose estimation without the need of real 6D pose labels. Leveraging neural rendering, we formulate a self-supervised solution for 6D object pose estimation by means of visual and geometric alignment. Our approach can be summarized as based on two main stages. In the first stage, we train our model using a large amount of synthetic RGB data. After this stage, our model can predict coarse pose estimates and object masks on real images. In the second stage, we self-supervise the model on real RGBD data without making use of any labels. To optimize the visual and geometric alignments between the model's prediction and the RGBD sensor, we make use of differentiable rendering. After self-supervised training, the performance on real images can be improved a lot. Our network is built on top of an FPN-based one-stage detector. We use ROI-align to extract ROIs from the fused FPN feature map, and then employ different branches to predict allocentric rotation to the centroid, the distance and visible mask of the interested object. Note that during self-supervised training, only the pose estimation branches are trainable. Our self-supervision consists of several constraints for visual and geometric alignment. As mentioned, given the predictions from an input sensor RGB image, we use a differentiable renderer to obtain rendered mask, rendered RGB, and rendered depth. Then for the visual alignment, we have three different losses based on the mask and RGB information. Since the predicted mask here is not perfect and we treat it as a pseudo-label, we use a modified cross-entropy loss, which calibrates the weights of the positive and negative regions. We use several color-based losses such as L1 loss, multi-scale structural similarity loss, and perceptual loss between the rendered RGB and the sensor RGB. For the geometric alignment, unlike the color-based losses, we want to explicitly incorporate the 3D information. Hence, we minimize the chamfered distance between the back-projected point clouds from the rendered depth and the sensor depth. Thanks to physically based renderings, the predicted masks on real data are highly accurate, thus can be reliably used as a self-supervision signal. We can show that our self-supervised loss is indeed highly correlated to the actual 6D pose errors. We optimize our self-supervised loss on a single image with 200 iterations. We can see that as the loss decreases, the pose errors are also reduced. Our ablation study suggests that the mask loss and the geometric loss are the most important ones, and the overall best performance can be achieved using all those terms together. We also demonstrate that the performance of our model can be improved consistently with more real data. Compared to state-of-the-art methods on LineMOD, our Self6D outperforms all the other methods without using real pose labels, and can almost halve the gap with respect to fully supervised methods. Interestingly, our method is even slightly better or on par with some early fully supervised methods. Here we show some qualitative results on LineMOD, Homebrewed DB, and LineMOD occlusion datasets. As our method is suitable for conducting synthetic to real domain adaptation, we also show that Self6D can successfully surpass state-of-the-art methods on the cropped LineMOD scenario. In conclusion, we propose Self6D, the first self-supervised monocular 6D object pose estimation approach, which enables learning from real RGBD data without the need of 6D pose annotations. Leveraging neural rendering, we can enforce several visual and geometrical constraints, resulting in a remarkable leap forward compared to state-of-the-art methods using purely synthetic data. Moreover, we can notably reduce the gap to state-of-the-art for pose estimation based on real pose labels. In the future, we want to remove the need of depth during self-supervised training. Also, incorporating 2D detection into our self-supervision is an interesting direction, as this might reduce the errors from the 2D detections and allow end-to-end training. Thank you for your attention. Our code for differentiable rendering is available in GitHub.